Hi, my name is Anthony Simmons, and I served as Paramount Engineering's project manager for the State Route 94 and Interstate 15 Interchange improvement projects. Currently, the SR-94 is a congested facility which operates at low levels of service. This leads to safety concerns because the accident rates are higher than the statewide average. In addition, there are ramps connecting the SR-94 and I-15 that exit from the number 1 lane, also known as the fast lane. The project's purpose is to increase the person carrying capacity during the peak periods and to enhance safety and operations on the freeway connectors while accommodating the regional needs by meeting the goals of the 2043 design year. The objectives of this project are as follows. Remove the left-hand connectors and replace them with ramps which exit from the right side. Maintain or improve future traffic levels of service and travel times. Help achieve the goals of the 2030 San Diego Regional Transportation Plan, and minimize environmental and community impacts. The task proved to be challenging due to the existing conditions of very tightly spaced on and off ramps, making it difficult to find a suitable exit location for the ramp connecting the westbound 94 to the southbound 15. This interchange improvement presented considerable structural, geotechnical, and environmental challenges as well. Thanks to the efforts of my fellow members, we were able to overcome these challenges and meet our objectives while complying with the Caltrans standards and meeting our clients' needs, as this video will illustrate.
To better find a solution to our problem, we designed several alternatives. Alternative 0 here shows our existing conditions for the interchange with the current left-handed connectors. These left-handed connectors are non-standard and have a tight radius that cause safety issues due to the speed of the driver exiting the freeway. These connectors are all one single lane, which clearly limits the ramp's level of service. When driving these interchanges, there is noticeable markings on the ramp barriers which clearly show drivers making contact with the walls due to the quick drop in marked speed. To solve the problem, we developed our first alternative. In this design, we proposed a redesign of the exit for the 15 South coming eastbound on the 94. With this new design, we also were able to create the exit for the 15 North as seen in the plan view. Due to limited space and no logical acquisition of right-of-way, we were unable to add any lanes to the 15 South interchange. However, heading north, we were able to achieve a 2-lane interchange staying within Caltrans' current right-of-way. This extra lane for the northbound allows for a higher level of service as well as an opportunity for a driver to pass the car in front if they feel necessary. The radius of curvature for this ramp is 1,150 feet, which allows for a design speed of 60 miles per hour per Caltrans Highway Design Manual. The ramp for the 15 South coming from the 94 West has a proposed exit before the I-805. The ramp is approximately 1.6 miles in length, but provides a second lane to once again improve level of service and allow for passing. This proposed ramp offers a smooth incline to clear all bridges and overpass that become obstacles down the road. The radius of the ramp at its tightest point is 1,225 feet, which would carry a design speed of 60 miles per hour. The interchange connects to the 15 South at the same point as existing conditions, which is critical since any further down the 15 would cause issues for use of the Market Street exit, which is a major surface road that provides access to various shops in the area. Our second alternative does not improve the existing 94 East to 15 South interchange, but similarly splits off for the 15 North. This alternative only has 1 lane ramp, so there is no level of service improvements. The proposed interchange for the 94 West to 15 South would exit right before the Home Avenue Bridge entrance to the 94. There would be a need of right-of-way acquisition for this interchange to be constructed. Once again, this interchange would only include 1 lane, so the level of service would not be increased and there would be no room for passing on the ramp. Though the cost for construction would be higher due to the length of the interchanges, alternative 1 was our choice for building. First off, the multiple lanes provided on the ramps increase our level of service, which is crucial on all transportation projects due to the growth of our cities. Secondly, there was no need for purchasing right-of-way. This helped save crucial money from the budget that can be used for the additional costs incurred by the interchange Another reason this alternative was a better choice was due to the ramp slopes. The location of the exit in Alternative 2 for the 94 West to 15 South required a slope that exceeded the 8% recommended, while Alternative 1 exited with plenty of time for a gradual slope to clear the upcoming bridges and connectors. The final factor that helped us make our decision for Alternative 1 was due to the weaving section created by the 94 West to 15 South proposed ramp in Alternative 2. The location of this exit is 386 feet away from the I-805 entrance to the 94. This distance would cause a safety issue as well as congestion issues, since there is clearly not enough room for drivers to get to their necessary lanes.
For the structural aspect of this project, I decided to use cast-in-place reinforced concrete box girders for the bridge deck. All reinforcement was done according to the ACI Code 318-11. 2 of the 3 overpasses will be 2 lanes wide and 1 will be 1 lane wide. This requires the use of differently sized girders. Section AA will be used for the 94 East to 15 North overpass and the 94 West to 15 South overpass. Section BB will be used for the 94 East to 15 South overpass. Due to the shear demand, the proposed girders will be thicker than the minimum as required by the code in order to allow for increased shear capacity. The dead loads modeled for the bridges include the concrete self-weight, the asphalt self-weight, and the guardrail. The live load was assumed to be 640 pounds per square foot. The dead loads were multiplied by 1.2 and the live loads were multiplied by 1.6 as required by the ACI code. The girders were reinforced for flexure and shear demands. The columns used to support these bridges will be placed 50 feet apart. The bent caps of these columns will consist of solid concrete and will extend 2 feet over the edge of each column. Although most columns in this project will be vertical, some will be inclined to avoid existing infrastructure. The interaction between moment and axial forces in these columns was taken into account. Where inclined columns could not be used, reinforced transverse beams were used. The foundations used to support the columns will be 15 feet in diameter and 48 feet deep. They will be reinforced for axial and shear forces. For the stormwater aspect of this project, I determined the temporary BMPs used on this project and the amount of permanent drainage to be used on the bridges. Due to the scope of this project, a large variety of construction BMPs will be used. Certain minimum specifications were required for the drainage infrastructure on the bridges. These minimums are well in excess of the maximum predicted drainage demand for the area.
For the State Route 94 and I-15 interchange, I was one of 2 geotechnical engineers for this project. I began by researching the on-site conditions of the soil. Here I was able to determine usable and reliable data to base our foundation design off of. After the foundation design was finalized, I aided and completed a geotechnical engineer's report containing the compiled findings for the on-site soil conditions as well as recommendations for the project site. A few brief challenges that I ran across early in this project was that I underestimated the time it would take to research the on-site conditions. In addition, the hardest part for me was coming up with both usable and reliable information for the structural engineer to base his design from. Once the geotechnical engineering aspect was complete for this project, I then submitted the findings, recommendations, and foundation.
I aided in the geotechnical section of the Interchange project as well. I started by helping research the on-site soil. Once the soil formation was determined, I began work on the foundation calculations. I helped to design an affordable, safe foundation to support the load, while working with the structural engineer of the project. Finally, I worked to complete a geotechnical report, which included our findings, recommendations, and supporting calculations.
I was in charge of the environmental part of this project. The study report I compiled discusses the environmental factors and issues in play for the proposed project. This project involves numerous environmental considerations in terms of the natural environment as well as the built. The study area intersects with areas of interest as they include historical, archaeological, and hazardous waste sites. Specific areas which require attention consist of the surrounding cemeteries such as the Holy Cross Cemetery, as well as trolley station stops, residential areas such as Mount Hope and Southcrest. The permits which were required for the proposed project are shown here. These included Section 7 from the Federal Endangered Species Act, Section 106 from the Natural Historic Preservation Act, and Sections 401 through 404 of the Clean Water Act. Mitigation efforts were carried out for the 5 different areas which are shown here. Mitigation is required for any impacts made on biological resources, temporary or permanent. Impacts include any changes made to wetlands, vegetation, regulated plants, and animals. Choyas Creek and Wabash drainage are the waterways which require consideration for this project. Preliminary structural designs sought the need for a column to be placed through Choyas Creek, but mitigation efforts were carried out by implementing slanted columns in order to avoid the creek as much as possible. Other mitigation efforts need to be taken for the biological well-being of the area by possibly carrying out construction outside of breeding season. Also, if any effects are still caused, then restorations and habitat enhancements are necessary. Further on, mitigation bank credits could be purchased at the accepted ratios of 2-to-1 and 3-to-1 for temporary and permanent impacts respectively. The Choyas Creek requires a quality monitoring and sampling plan in order to meet TMDL's requirements for zinc, lead, and copper. Regulated floodways and floodplains could possibly be affected by the corridor improvements. Therefore, a hydraulic study is required. Also, floodplain impacts could be mitigated through underground conduit systems and long-span bridges. A mitigation solution for the noise impact is a $5 million 2.1-mile sound wall which will run along the most impacted residential areas to decrease the adverse noise impacts which will be a result of the construction. Effects to the visual appeal of the surrounding area could be mitigated by implementing visually appealing elements through the construction process. Examples of this include applying the use of landscaping. Vegetation could also be applied to the proposed sound walls and to their surrounding areas which are to be affected. This would help meet the expectations of the local community. Lastly, in the case of identifying any historical resources, several surveys will be required. These include a data recovery plan, archaeological evaluation record, and archaeological survey report. Also, mitigation measures must be taken for any historical or cultural resources. These will be determined by the following surveys: the Historic Property Survey Report, Historic Resource Evaluation Report, and Area of Potential Effects. In terms of the social and economic advantages that are associated with the project, it begins with the fact that the current route is extremely congested and accumulates severe traffic during peak hours. Therefore, the project will help in increasing peak hour capacities and in turn enhance safety and decrease accident rates. Neighboring residents will be able to experience a decrease of noise and traffic in their areas. The project will also help provide drivers with a more pleasant, stress-free, and most importantly, a safe commute. Travel times will decrease as efficiency will increase. Also, the project proposes a positive economic impact. It will help increase employment levels as there will be many supplied jobs in order to fulfill all the aspects needed. The mitigation measures require the need of surveyors, experts, and contractors to implement the needed solutions. Many other aspects of the project obviously will also employ numerous people to carry out the assignments. The improved interchange will help with more timely and reliable deliveries and service. This will translate into a higher productivity for certain companies. On a larger scale, this is an extremely beneficial and important advantage for the city's economy. It is also important to understand that the advantages of this project will be more long-term than short-term and will be beneficial and significant, but will require some time to surface and peak.